Right, so as Mark said, what we're going to do today is go through modal analysis of components and assemblies. That was the original scope. What I've done is I've took it a little bit further and took it into looking at vibration, force response, whether it's random, shock, sine sweeps, etc. So I've put in some workflows to explain how you would do those as well, and what the options are within the Siemens portfolio. So it goes a little bit further, and the files I've sent out, you can use those as a starting point, or as Matt said, you can take what you've had previously and start and work with them. So let me first of all start and share my screen with my PowerPoint. And what I've done, the same as I've done on the other sessions, I've sent out two PDFs. One is the content of this PowerPoint, and the other one is the example where basically I've took out bits out of my PowerPoint and broke them out into two. So you've got the example, and if you like, the handout, which is all of the other slides other than the example. It's just the way I've done all of them. I'm just doing it for continuity. So my name is Mark Sharples. For the people who, there's a few people joined this session who haven't been on any of the previous ones. So welcome to you guys that have come on. I've used Simcenter, Siemens products for 30 years. So I've used Ideas, NX, VMAP, a wide variety of simulation tools. So I'm going to take you through the session. So today, the agenda is to go through modal dynamic solutions in Simcenter and explain what they are, what the options are. There's going to be a problem that we're going to work through, which is the files that I've sent you. If you've been on the first two sessions, you'll recognize the geometry. But on this session, I'm going to do some things slightly differently because I can't use the same assumptions that I did on some of the previous simulations. So we'll have a look at that, and hopefully I'll explain that as we go through. We're going to look at the process, which we've done on all the others. So, what is the process for completing a modal analysis and a dynamic analysis? Then we're going to break out, do the modal, then do the dynamic. I'm only going to do the frequency response in terms of taking you through all the picks to do it, but I will show you some results from transient and random. They're just extensions of the same process that I used for frequency response. And then we'll have some conclusions at the end, just explaining, what you kind of need to understand when you're doing this analysis. What are the drawbacks? What kind of things you need to be aware of in terms of, the amount of volume of data that you're generating, etc. We're going to go through that. Okay, so within Siemens, if you've got the Nastran basic solver, which everybody will have who can do a Nastran solve, like a linear static, because within there you've got modal analysis Sol 103. So we're going to use that and go through and do a 103 solution today on the bracket that we've used previously. So everybody can do that. Everybody would have access to that license. Within Siemens, we also have Simcenter 3D Response Dynamics. This is a product that originated in Ideas many, many years ago and was transferred through into NX Nastran, the Siemens portfolio. And that is included in your token licensing scheme that we've mentioned in the previous discussions. And it utilizes 42 tokens. And it doesn't have a prerequisite of Nastran Basic. So what you would do with the response dynamics is you would solve using your Nastran Basic solver, get the results, then you would do a response simulation, which then just uses the tokens that it needs to do the response. So it's a little bit more efficient in terms of token usage. So that's the one that we're going to go through today. Within Siemens, we also have Nastran Dynamic Response, which is the Nastran Dynamics capability. This is a separate license within the Siemens portfolio, and it utilizes 35 tokens, but it does have a prerequisite that it needs access to NX Nastran Basic. So if you've got standard Nastran basic solver included in your licensing, then it's only 35. If you don't and you're relying on the tokens to do the Nastran basic, then you would add the 82 to the 35, so you'd need 150 tokens to do this kind of simulation. The advantage with Nastran Dynamics, it also has the ability to do super elements. It can do distribute memory parallel. It's got a lot more capabilities in it to allow it to make it very scalable for very large dynamic problems. And all of those additional bits of functionality like super elements, DMP, they all consume tokens. But we're not going to cover that in this particular session. But you'll see where they are in the user interface, so there's nothing to stop you trying to replicate what we're doing with response dynamics using the Nastran dynamics if you wanted to, and you've got enough licensing to do it. So the Nastran basic can calculate normal modes and frequencies. So that's going to give you the mode shape of a structure and at what frequency that will happen. And that's something that we can use very easily and readily. It calculates displacements and stresses and other parameters, but none of these values are valid or correct. So all you're going to get from a 1 or 3 normal modes is the mode shapes and the frequencies. Stresses, displacements, you have to just take them with a pinch of salt, ignore them. They're not really valid to make any kind of decision on your structure. If you want to get real displacements and stresses, then that's where you need to start and do a Nastran dynamics or response dynamics to start and get realistic stresses, realistic deflections of your model. And that's what we're going to cover in the second part of the session. Any questions about what I've gone through, first of all? Everybody okay?
Yeah, thanks.
Yeah. So let's look at our problem. So for people who have done the first two, it's kind of looking familiar. I didn't change the colors. I was going to try and make it a little bit more interesting, but we're still back at the bracket with the wheel attached. So what we're trying to do in this particular part of it is we're looking to see, well, what are the mode shapes and what are the resonances of the bracket? That's what we're trying to determine this time. And also maybe how would the bracket respond to some dynamic input? So if I was to put in a shock pulse, for example, or put it on a shaker and do a sine sweep, or I might have some random spectra I want to put into it, how would the bracket respond to those? And what methodologies would we use to do those kind of simulations? So that's really where the problem is starting to be defined. So what I've said here is, well, if I do dynamic inputs, if I do a frequency response of 1G, 20 to 2000 Hertz, what happens? How do I put that in? How do I make sense of the results? What is it doing? I may put a transient pulse in 20G for 10 milliseconds and see how the structure responds. Does it ring? Is there any resonance as a result of putting in that pulse? Or maybe looking at a random spectra. In this case, I've just done a flat spectra, 0.001 G squared per Hertz between 20 and 2000. So these are maybe typical dynamic inputs that you might need to put in. Usually if you're looking to do vibration dynamic analysis, usually this is something that will be specified in a spec to say it needs to withstand a certain pulse in a certain direction or a certain spectra in a certain direction. It might also need to be dwelled at certain frequencies for a period of time. And that's kind of what we're going to do with the dynamic analysis. So here in the past, 2 examples, we've used symmetry to represent the bracket. In this case, we need to think about and say, well, can I still apply that axis of symmetry when I'm looking to work out the mode shapes of the structure? And the answer to that is no, we can't, because that symmetry plane is stopping the bracket from moving across the symmetry plane. So when I look at the normal modes, I want to see that bracket not just behave in bending, but I might want to see torsion, and I also might want to see it move side to side. And I couldn't do that if I had a symmetry constraint stopping that from happening. So in this instance, we're no longer going to utilize the symmetry. So now we're going to have to mesh the whole bracket. And also what I've done in this instance is I've gone ahead and meshed the wheel, the hub, and the attachment nut at the top. So we've now got the whole thing modeled, and now I'm going to show you how we can start and connect that together. Hence the reason we're looking at doing modal analysis now, not just on a single component, but on an assembly. In this case, the assembly with the 4 components that we've had previously. So if we follow the examples as I've done previously, in terms of what I'm presenting you, everything with this sort of orangey background, that is what's in your example PDF. I've just kept them all in the PowerPoint so you can sort of see where they fit in context. And I don't need to jump in and out of different PowerPoints. So here's my NX session. If I open the PLM file that I sent you, so you can see we've meshed all of those entities. So under here, you've got all of the different parts of the structure. If you wanted to, you could change the colors. And here, so you can tell which one's which, maybe a bit more visually, so you can sort of do these kind of things if you want. So you can also edit the display and maybe put on black edges to your model, like so. You know, so you can sort of change the way it's represented, but ultimately now we've got visibility of it. What I've done in here is I've also used 2D meshes in here to seed around our fillets. In the past, we used adaption to work out what refinement we had. This time I've meshed those surfaces, but what I've done is here you can see there's not a solid dot against them. So what these are, do not export to the solver. So here I've put a seed mesh on to control the mesh, but I don't want those to go through into my solver. I only want these components to come through into my solver. So it's a slightly different model to the way that we've done some of the ones in the past. Okay. So here you can see we've got our material, we've got our aluminium for all of the components, and that's really the first part of the example. So because we're going to do the modal analysis, we need to understand how is the assembly connected, where is it constrained, is it free? So free is a term that you might have come across if you're used to doing dynamic analysis. That is something where you don't hold your structure, you just want to hang your structure off some soft bungees, for example, and you might hit it with a hammer, and that would be a free kind of analysis where you take out the constraints and you just want to see the behavior of your structure without any real constraints. Then you can add in constraints once you've correlated or understood the behavior of the structure. So there's a few different things that you might want to consider. So the process, you would create your mesh like we've done previously. Then we'd create a sim file and apply boundary conditions to it. And then we'd solve it for modal or modal with response dynamics. And I'm going to show you the difference and how you follow that process through. You would review the mode shapes in the post processor, then apply your dynamic inputs, solve it, and then again, post process those results. So then you would start and get realistic stresses, deflections, etc. So let's go ahead and start and do that. So the first thing we need to do is create a sim file and tell it we want to do a 103 analysis. So the way we would do that is we can right click here and say we want a new simulation, or we can go to the top left and say new simulation. Here we choose it from a standard template. I'm just going to put this into the folder that I'm working with just now, like so. It says I'm going to attach this sim to your FEM, which is okay. And now we're looking at the analysis. So here, if I call it normal modes, I'm still doing structural and Nastran, but this time I want to do a 103. But notice we've got other 103s. We've got flexible body, response dynamics, super elements, etc. So here we're just going to do a standard 103 eigenvalue solution. And then we create the solution, and okay. Here you could create different steps. So you could do a static subcase where you can maybe apply some load and then run your dynamic analysis. So you've got other options under here. We're just going to solve for normal modes, like so. So I just accepted all of the defaults. So here I've said basically choose 103 and then set all of the defaults. And what you should see is this in your simulation navigator. So here you can see we've got objects, constraints, we've got a normal mode subcase, and that's basically what we have. If we go into the normal mode subcase here and we create loads, here we can only do bold preload. So one of the things that you'll notice from a normal mode analysis, you can't apply forces to it within the normal modes analysis as a normal modes analysis. You can only apply bold preloads, for example. Okay, so we've created that part of it. So now I'm just going to hit solve in post-process. So in here, I haven't got any constraints. I haven't got anything on my model. If I go ahead and just hit solve, accept the defaults, and then say solve, it will go away and solve that problem. If you're trying to do that with a linear static solver, it would fall over because it'd say you've got singularities, you've got no constraints to get rid of the rigid body motions of the structure. If you do a 103 simulation, it can handle the fact that you've got rigid body motions. So it will solve even though you haven't got any constraints on it. And it's one thing that you could do if you had a 101 linear static solve that wasn't solving, you might do a solve 103 to see where it's not attached. So it's actually a way that you could debug a linear static solution. But in this case, we're looking to do it to work out the natural frequencies and the behavior. So here, I'm not going to look at the list files. I'm going to go in and look at my result. So now notice in here, I've got 9 modes that are all nearly or around 0 Hertz. So these are all rigid body motions. So here, if I look at my first mode and we animate, you can see here we've got a mode for our bracket. And as we step through, we can see we've got a mode of the wheel, one of our locking bolt, another one of the wheels. So here you can see the mode shapes, but they're not joined together. And then it's got a mode here, which it thinks is a joined up mode, but it's just another mode of our bracket. So really, we haven't got anything of any sense out of that solution because we haven't joined all of these objects together in some fashion. So if you've got multiple objects, you need to link them together in the either by forcing the mesh to be coincident or you would use glue or contact or some other mechanism to join them together. And that's what we're going to do next. So here, as we're seeing, you can see all of the rigid body modes. So what I'm going to do now is go in and add in some gluing to try and join these objects together. So let me show you how you do that. Here, so here I can just switch off my mesh. I'm not deleting it, I'm just switching it off because I don't really need to do anything with it at the moment. And underneath my object types, here I've got contact or glue, either surface to surface, edge to surface, or edge to edge. Whatever you see here, or what are possible with the solver that you've got active, i.e. normal modes. If I change it to be something else, then I might see a different list of capabilities underneath here. You only see the icons that are related to the solver that you're doing. So notice here I can't apply forces, etc., like we could previously, because 103 doesn't allow us to do that. These are the only boundary conditions we could apply from a loading perspective. Okay, so let's do surface to surface glue. At this point, we could just simply blindly say automatic pair and pair everything within this 1 millimeter tolerance. What we're going to do is be a little bit more strategic. So here we're going to say, when we do the pairing, it's now saying, what faces or bodies do you want to use? So what I'm going to do is I'm going to change this filter to face. And now I'm just going to pick the faces that I'm interested in. So I might want those two. I might want this face here. I'll take I can take that one as well, actually. Take those ones. Take all of the surfaces that I'm interested in. So what I'm saying here is I'm choosing all of the surfaces that I want to consider to glue together. If I just took everything, then I would start and glue these internal cylindrical shafts together, which I might not want to do. So here I'm just being specific. And again, I'll show you in the PowerPoint what I do. So here you can see it. We can do it as a face pair from our selected objects. So if I OK that, and then OK, what it's now done is it's created 3 surface to surface glues. So if I highlight these, I can do show only. And that will show me where all my glues are. So I've glued here to here, I've glued in here, and I've glued there. So now I've put gluing in between all of those surfaces where it's clamped down by my locking nut on the top. And they were automatically created for me, but I just told it what surfaces I wanted to consider. If you do Control Z, you'll get back to what you had, and if you don't want them on the display again, you can just switch them off. What I'm also going to do at this point is I'm going to put some fixed constraints on to these locations. So I'm actually going to fix it this time. Like so. And then we can solve. Okay, so in here, I've shown you the picks that I do to create the glued surfaces selectively. Here you can see the results when I did the show only. And these are the ones that I picked, where I've picked the surfaces. And then I'm going to solve in post-process. In the example, I get you to solve it without having the 4 fixed holes in place. Then you put the 4 fixed holes in place. So here you can see, if I didn't fix the holes, I still have 6 rigid body modes. So I have translation in X, Y, and Z, rotation about X, rotation about Y, rotation about Z. So they're my 6 rigid body modes that I haven't constrained with any constraints. If you then fix it like I've just done and look at it, now you see these rigid body modes are removed, and now you'll see the real modes of the structure, starting from mode 1. There are other ways we can do this. We can filter out the rigid body modes in the solver if we wanted to, but in this case, I'm not doing that. So now we can come in, you can see our modes. We can look at the mode shape. So here when you animate it, you can see, all of our structure is now moving together. And we can step through the modes. So that's a vertical mode of our bracket. And then here, we're seeing, like a side-to-side motion, and that's one that I wouldn't have captured if I kept my symmetry plane in as I used in our nonlinear and our linear solution, because that symmetry constraint would have stopped that particular mode from being captured in the normal modes analysis. And here you can see, slightly higher orders, and as you step through them, you can pick all. So here you're getting, mostly a mode of the wheel. There's not a lot of motion on the bracket. It's predominantly a main resonance of the wheel. And then you get the opposite diagonal to that on the wheel. So these are at similar frequencies because this wheel has got similar stiffness in this direction and in that direction. So that's why we've got two mode shapes that are very close together in terms of frequency. Okay, so you can look at the results of the animations, look at the frequency and the shape. Notice you do get deflection, so you can come here and look at the deflection, and you can look at stresses. But as I mentioned earlier on, these stresses are not real stresses because there's no scaled input, there's no regular input that it can scale these stresses against or deflections against, and that's why you would need to do a forced response to do that. Okay. Everybody okay with what I've done so far? Has that made sense? Everybody all right with that?
Yep.
Yeah.
Yeah.
I mean, commonly what people would do, you do your normal modes, you look at the frequencies, and then if you've got a certain excitation, you would then either try and make it, so stiff that it wasn't excited. Then you could do a 1GX, YZ, standard linear static load, and then start and scale that to give you realistic stresses. That's kind of a typical workflow that you might do. What I'm going to do with it now is I'm going to prepare it and do a Sol 103, but for response dynamics, to then allow me to do that forced response. So I'm going to show you how you would do that. So what I need to do is go into the FEM and then create some 1D connections. So again, I'll create them as we go through and try and explain what they are. So you go into the FEM, and we can hide them off because we're not really needing to see them. So what I want to do now is I want to take these four holes and I want to put an RB2 element in, a rigid bar element, which basically means whatever the center point does, all of the leg nodes will follow. So let me show how you do that. You do a 1D connection. Here I'm going to do it from point to face. I've selected RB2, but I could do other things. We're just going to use RB2 in this instance. I can pick here like so, and then I can choose the face and it'll create it. Do the same for this one. And here I can just put them in the same collector. Here to here. And then again from there to there. What I always tend to do here, just so you can physically see, is I'll edit the display, change them to be, some really bold color, And because I'm getting old and blind, I make them thick as well so you can see them. Okay, so that's an RBE2. So basically what that means is whatever this middle node does, all of the leg nodes have to follow. So if this node moves 4 mil in X, then all of the other nodes will move 4 mil in X, because that element is a rigid element. So it's rigidly constraining the hole, not to change shape, or basically whatever the middle point does, they do. So what I now want to do is I want to do another connection, which is a point to point. So what I want to do now is I want to create a point which is between 2 points. So I can see it between that point and that point. So here, and then I can see it translated a distance. So here I can see -30, like so. So now that creates a point which is in the middle of this face, but 30 mil off the surface. Then I can pick the points I want to connect it to. So here I'm just going to pick these points. So now I've created an RBE2 element where basically whatever this point moves, that point has to follow, and whatever that point does, all of the leg nodes have to follow. So this is quite a common workflow when you're doing enforced inputs. So I've created that to allow me to start and apply my inputs to my structure. So here you can see, I'm doing points to face. I create these connections. Then I create my excitation point, which is done using point to point. And then we go in and create a response dynamics, 1 or 3 for response dynamics. So in these picks, I haven't got a lot of content on the example, but what you need to do is follow through the 1D connections to define them. Okay, so now when I come into my sim, here you can see we've got our connections come through. So what I want to do now is a new solution. So I'm going to do a new solution. So this is my response dynamics. So here I'm going to do 1 or 3 for response. And I'm going to create a solution and take the default. So here you can see I've got other capabilities now. I can do a static offset. I can do stress stiffening. I can do dynamic effects. And in my dynamic effects, I can create a whole load of loads now. So because this response dynamic is going to allow us to apply loads, scale them, and then allow us to factor them with a given input, whether it's a transient input or a random input or a frequency input, then we can get realistic stresses out of it. So this one gives us a lot more capabilities than just doing a normal 1 or 3. So what I'm going to do here is I'm going to do these same glues. So what I can do is I can highlight the glues and just simply drop them into there because I don't want to have to redefine them. In terms of constraints, I've got a constraint here which is fixed. What I'm going to do is create a new constraint. So here I can create a new constraint that isn't a fixed, but is what is called an enforced motion location. So if I do that, then I can pick my point and I can set all of them as being enforced, like so. So it means now I've got an enforced motion location defined here. I haven't put any other forces onto it, but I could do. And then what we're going to do is simply solve it. We'll solve it like so. So here I create the new solution. I drag the glues. I put the constraint, which is the enforced motion constraint, as we did, and we put that at this point on our spider. So what that basically means is I can enforce an input here, but it's going to go in all 4 holes. And then we're going to solve it and look at the result. So let's see what we get. So now we've got a result. I come into here and I notice I get the same mode frequencies as I got previously by doing it with the normal modes. The difference is I get constraint modes, and if I'd applied forces, I would have attachment modes as well. So these are things that will allow me to kind of scale the input to do the forced response calculation that I want to do to get the right stresses or the right deflection. So I will get other information, but the actual mode shape is the same. So here, if we do two side by side, and we take our original one where we did it just with normal modes, you get the same result. I've just set it up in a different way so I can use it a bit easier when I'm starting to do some response dynamics. Okay. That's really where we've got up to. Now, to do the dynamics or response dynamics, we're now going to start and look at our frequency response, and we're going to start and define that. Before I do that, is there any questions on what I've done so far? Is everybody quite happy with what I've done?
Yeah, no, that's fine.
Yeah. Okay, so what we want to do now is we want to start and do a physical response of this structure. So if I was using the Nastran solutions to do it, I would say a new solution. I come in here and then I've got direct frequency, direct transient, all of these options, so 107 to 112 will allow me to do that using the Nastran solver. As I mentioned in the original preamble at the beginning, before we went in to look at the problem, we're not going to cover that in this part of the analysis, in this particular session. Those are where you would need to use the Nastran dynamic solver, which is an additional license. So, and you could try and repeat it with these if you wanted to, but we're not going to use those. So if you don't want to use a new solution, which is one of the Nastran solution sets, what you can do is you can choose a solution process. So in there, we did adaptivity when we did the linear static analysis to work out, well, what mesh do we need to be able to get the right result? There's also some other processes under here that you can follow through. If you've got token licensing, you can do pre-test planning, you can do correlation, you can do all sorts of other things under here as well. But what we're going to do is response dynamics. This list will change depending on the version of software you have. If you have towards the latest, then you'll have a much bigger list of capabilities in there than what you would have if you say we're at NX12. You wouldn't see all of those capabilities at NX12. So here, if we go into response dynamics, so here we can so you can call it whatever you want. Here you choose the solution that you want to attach it to. So now what you'll notice in here, we've got under the model representation, you can see we've got 10 modes. If I minimize the simulation file view and I bring up the response dynamics view, what we can do now is we can go into this, and what this will tell us are these are the frequencies. This is the damped frequency, but here we haven't applied any damping. So these are the undamped frequencies that you're going to get. But what we can do is introduce damping. So in reality, you wouldn't have a system with 0% damping. You would have some percentage damping included. And we're going to look to do that. The other thing you get from this is the effective mass. So this will tell us how much of the effective mass is being used in each of the mode shapes. So if we look at this mode shape here, and here, the ones in the wheel, they don't really have a lot of effective mass, i.e. they've got 0. So what we could do is we could ignore that in the solution. because they're not contributing significantly to the response of our bracket. Same with this one's relatively low, same with this one. But if you start and look at these mode shapes, this one's very dominant in X. This one's very dominant in Y. These ones have got values in X and Y. So you can pick up how effective the mode is. What's its effective mass? And at the bottom here, it lists what the total effective mass is. So we've got 88% in X, 91, 89. And as a rule of thumb, you'd like to have over 90% or 95% of the effective mass captured by the modes that you have. So here I've only recovered 10 modes, which maybe isn't sufficient to represent all of the effective mass. So I might need to recover more mode shapes to allow me to do that. In this case, we're not. We're just going to run it with the 10 modes that we've captured. But there's a term called modal sufficiency, where that means you need to have enough modes to accurately represent the effective mass of your structure. Okay, so let me hopefully help you with the example. So here we create the normal modes. I clicked on the mode shape, and then I can go in and we can look at the effective mass, and then we can start and apply some damping to it. For typical metal structures, it might be somewhere between 2 and 5% is a reasonable damping value. But if you have a laminate structure with epoxy bonds, then maybe it would have a different damping parameter or a damping percentage, because you've got damping and other effects as a result of the structure. So what we're going to do here is we're going to run it with 5% and 2% and just show you what the differences are. So in here, you would right click on the normal modes and then apply your damping percentage. So here we can right click there, edit the damping factor. We could also start and calculate it from the damping matrix, and there's other things we can do in there, but all we're doing here is we're just applying the value. So here we can choose it. We want viscous damping, and we can see it 2%, like so. So now you can see we've got 2% in here. Okay, so now we've applied our damping. The next thing that we might want to do is put on some measurement locations. You don't have to do this, but this is useful if you're going to try and correlate it with something that you might have on a shaker, or somebody might have given you some responses that you want to check your model against. So that's what we're going to do next. So let's put on some acceleration sensors, for example. So here we can see a sensor. We want a new sensor, and then we can decide where we want to put them. Here you can decide whether it's a displacement, velocity, acceleration sensor. Let me put the mesh on so I can see, and we'll in that sense. So here you can decide what component you want to measure in. So you could have a unidirectional sensor. So if it's just a single accelerometer, that's not a triaxial, you might put that on your structure and it would be normal to the face that you put it on. Or you can define what the component is, whether it's an X direction, Y direction, Z, etc. What I've done here is I'm just assuming I've got a little tri-directional sensor that will measure acceleration in X, Y, and Z. And here it's saying pick a node. So what I'm going to do is pick some points where the sensors are positioned. So here I'm just picking some arbitrary points. There are ways we can control the mesh to make sure the mesh is in a given location, so we can relate it tighter to maybe what we're getting from test. So here we put some on there. We might put some here on our bracket. And what I'm also going to do is put one here near where we've excited it, like so. And what that does is, you can see it puts little sensors on. If you go here, you can edit the style, and we can change this to be bigger. So again, if you're blind, or you need to be able to see it a little bit bigger, you can do that. So you can see where these accelerometers are going to be placed on your structure. The other thing you can do here, which I haven't done in the example, but you could position a strain gauge. So it could be a rosette, you measure in stress, and you can position strain gauges onto the structure as well. So again, if you strain gauged it and you want to compare your model with strain gauge information, then that's what you would do here. Okay. So here I've put on the measurement locations. Now I'm going to start and create an event which will allow me now to start and get the response to some given input. I'll show you how we do that. So right click, we want a new event. Here you can choose whether it's transient, frequency, or random. In this case, I'm only going to do the frequency, but I'm going to show the results from a transient and a random. You can also do response spectrum, where that will limit the input to give you a certain value on your structure. So some specs say, you know, the maximum value on my structure is X, and you vary the input to maintain that criteria, and that's a response. So you can have like a shock response spectrum or response spectrum. DDAM is a military standard from the US. So that's something that the DoD use in the US for, I think it's ship-based structures, but DDAM is a specific kind of an event. So what we're going to do here is frequency. You've got different options. We're just going to take the defaults here. I put in some additional spectral lines so I can see my curves a bit smoother. Here we can have different spectra that are either even or uneven. I'm going to do it as uneven because it's easier for me to define the input. But some instances you might want to do it as even. So here we've got our excitation. Then I can right click, new excitation, and I can put in a translational input. So when I do that, so here I can sort of put my frequency, 1G in the Z direction. And here we can choose an enforced motion location. If I go here, I can graphically pick it, or I can go and list it here, and it lists whatever I've applied as an enforced motion input. And that's why I did that within the FEM when I went in and created this spider network and an enforced motion to allow me to pick that point using this form. It just makes that process a lot easier. In this input, it probably isn't going to make much difference, but if I was doing random, it would, because if I try to put the random into all four holes, I would then have to phase them all together. Because it's a random spectra, I wouldn't necessarily be putting the same input into every one of the holes. So I'd need to kind of cross-correlate them to get the right value. Where if I've only got one point and I put a random input in, then all four holes are fully in phase and using the same input. And that's why we tend to do it this way. It, again, just makes it a bit easier. So here we're going to do it in Z. Now we can come here and create a function. So we're in response. I want to create a new function. Here we can give it a name. We can define the axes. So we've got one of them as frequency. Here we can say we want acceleration in terms of G. Then we can come into here and we can import it from a spreadsheet. You can digitize it on a plot. All I'm going to do is just a simple key in. So here I'm going to do whatever my input was, which I can't remember. So here you can see we pick the translational. We're in the function manager. So here we're going to do 20 to 2000 at 1G. So here we just simply type 20 hertz, 1G, 2000 hertz, 1G. Like so. And that basically gives us the input that we're putting into the Z direction. Like so. So now we've got our input. And that's basically what we're doing here. Once we've done that, if we right click, we can then go in and evaluate sensors. And then once you do that, you can pick the sensors that you've already created to get the results for. So let me show you how you do that. So here we can now, once we've got it, we can see a right click, evaluate sensors. Here we can see a graphical or from a list. If I do graphical, here it'll just pick all of those sensors that I want to get responses for. I can give it a prefix. So here I can call it frequency 2%. And I've toggled on store to EFU. This is an associated function file, and hopefully that'll make sense once I show you how you might use it. So I toggle that on as well. So when you OK that, it now says, do you want to display it in this window, or you can pick a new window. If I click new window, and that's now going to put in all of the responses. So all of my sensors in all three directions. So now you can see the responses of all of these points to my given input with 2% damping. And here you can see the functions are listed, so you can go in and just right click plot, and again plot it to a new window, so then you can see what that response is for that particular location. So here you can see where you get it for all of them. Once you've got them, then you can go in and start and look at the responses. So what I'm doing here is I'm obviously at resonance, i.e. at this particular frequency, I want to work out and evaluate maybe what the deflection or stresses or whatever's behaving at that particular point. So here, if I was to go in and probe it, you can see I'm getting something at 120. So I'm getting 31G, but I was putting 1G in. And then here, again, at another frequency, which is 246. So if you notice it here, I'm exciting in the Z direction. So I don't really get anything with my first mode, but my second mode has a Z component. Therefore, I'm seeing more of a Z response when I'm shaking it in the Z direction. So this first mode isn't really getting excited because it's mostly a mode that's excited in the Y direction, not the Z. So here again, here you can see this one, the 247 is a very dominant mode in the Z direction. Therefore, when I excite it in Z, then again, you'll see that it's causing me a resonance or giving me a peak. So you can relate what you get with effective mass to the response that you get from your structure. And then you could go ahead and calculate the physical displacement and response. So let me show you how you would do that. So here we've got the response. So what you can do now here is you can see I want to get the contour results, response. And here you can see what result you want to get. So here we can say cent, whatever you want to label it. We can choose the elements we want to calculate it on. So what we could do here, switch everything off and then maybe switch on our bracket. So then we can just drag a box over all of those elements. So we'll create it on all of those elements, stress and displacement. And now it says which point in the frequency spectra between 20 and 2000 do you want us to calculate the deflection? So here we could just load a plot and pick the peak, or we can go to natural frequency. And now if I pick here, I can say, well, I want to calculate it at 121 and 247. So now that's going to go ahead and calculate the result at those two frequencies. So if I OK that, it'll now go away and calculate the response. So now we can look at the deflection. So now we can see the deflection of our structure. Like so. Which is the real deflection at 120 hertz. That's what we'd be getting. The only thing that you're finding here is because this point is where we're exciting, and that point might be moving a significant amount. In this case, it's saying it's moving, 0.017 as a physical deflection, and then we're getting some amplification to the end of the bracket. So what is quite common, you might come into here and decide you want that result relative to a particular point. So here you could pick the node that you want to use. So now, so you can see what the physical deflection is in terms of amplification. So assuming this is 0, i.e. that's, that input has been taken out of the equation. This is the relative deflection between the input and what we're seeing at this point. Like so. And you can also look at the stresses, and you can see what stresses you have in your structure at that particular frequency, which is the 120. If we go into the real results in here for the event, we've got the results for both. So here you can see what deflection you get at the other frequency. So here you're recovering the data and then looking at the result for whatever frequency point you're interested in. So if you had this structure and in your spec it said, do a sine sweep, work out where your resonances are in Z, then dwell at 120 hertz and 247 because they're the resonances for a period of time, then this would give you an idea of what the stresses and deflection are at those spot points that you're exciting it at. And that's kind of why you would do this analysis. Any questions around what I've done there? Or is that okay?
Yeah, it's okay.
Is that all right? Makes sense?
Yep.
Okay.
Yeah.
So here you can see we've got the responses. And here you can see we've got the two results, which we can go in and start and look at. And then I could vary the damping. So if I change the damping to be 5%, then here you can see how the response is changing based on the damping that I apply. So let me show you how you would do that. So what you could do with this event is simply clone it. Take the 2% and clone. So now we can go into these modes. We can edit the damping factor. So we can go and say 5%. So here we've got all of the sensors and everything still defined. Yeah, we've got our response. So here we can see evaluate sensors. We can pick the graphical selection. So here we can pick those ones. Call that 5 so we can tell the difference. So what we can now do is if we take one of these responses and plot it onto a window, and then we can take off that same point, but from our original. Yeah. Yeah, so here you can see the difference between our 2 and 5%. If I double click onto here, then I can change the units to be G. That makes more sense. Like so. So here you can see what effect the damping has on it. So with 2%, I get a bigger peak. With 5%, then it's less. If I was to do it even further, So I could have maybe a more heavily damped system. Then I can work that out as well. So again, we could clone. Maybe for a very, large 15% damping. Value our sensors, like so. So here you can, so you can start and look at the response. So now let me just put on this one. So you can see the effect of what, choosing different damping parameters. Like so. Yeah, so you can see the effect of damping. Okay. So what normally would happen is, you would maybe choose the worst case damping parameter, get the values. Then when your structure is built, you might put it on a shaker, do a sine sweep, work out what the Q is. So then that would work out the damping ratio, and then you would apply the damping ratio into your model to maybe refine your model or your assumptions. But typically for a metallic structure, it would be between 2 and 5. Okay, so here I varied the damping. What we can also do is maybe define a transient pulse, put that into the structure, and then evaluate. So here I'm putting in my 10 millisecond pulse, and then I'm solving it for a period of time. So here you can see how this structure would ring with a transient input. And obviously, if I tuned this pulse to correspond with 120 hertz, then you'd see a much bigger amplification, because it would be at the point where I'm exciting that resonance of 120 or the 247 in the vertical direction. Here I also did the random. So I put in my power spectral density. The difference with random is when I did the frequency response, I looked at the values at 120 hertz and said, well, what is the peak acceleration or the peak stresses at that point? If I'm doing a random input, what I would do is, because it varies randomly over the whole spectra, what you do is you look at the power spectral density value. So in this case, I've got an RMS value of 2. So that would be an acceleration of 2 as an RMS. If I wanted the peak acceleration, I would multiply that by 3 because of 3 sigma. So 90 odd percent of the 98.9, whatever it is, percent of the time, that would be the biggest peak, i.e. 3 sigma. So if you're using random spectra, you're looking at the power under the curve to give you the RMS, and then you're scaling it by the sigma, 3 sigma usually, to give you the peak for peak stress or peak deflection or whatever you want to look at. You want to see those models, or are you quite happy with what's in the PowerPoint?
Yeah, no, happy with that.
That's all right.
Yeah,
It's the same process, really. I can show you how you access it, just to remind. So in here you would when you create your new process, well, what you could do is actually you could do it underneath here. If you go to your 2%, here we've got an event, which is our frequency in Z. We could create a new event. That's a random, and then we can define what the random input, or we can do our transient and define it there.
Okay.
So when you do that, now you've got an event that you can decide where you want to put it in, but now it's going to be a transient or a random or whatever input you want. So it's the same process, really.
Okay.
The only thing is what you've got to be careful here is if you're doing a random and you request loads of information out, then it could take a while to calculate unless you use maybe fast RMS or other methods. So that one will tend to be slow if it's going away to calculate every bit of result that you're going to extract. So that's why in my particular case, I was just selective in here. So I just chose a portion that I was interested in. But you could do it over the whole piece if you wanted to. So if I was to look at an element here, I could plot it. And if I looked at the RMS value, that RMS value would correspond to the stress that I'm calculating here. Let me maybe show you that. If we look at it, say from our frequency response point of view, so here we've got our responses for the frequency. What you can also do here is get the elemental value. So when you pick an element, you can see give me the stress. You can evaluate the maximum and then store it. So here, if we just graph that. So that's telling us what the stress is in that element for our given input that we've defined. So if you were to look at the stresses that you see when I recover the stresses down in here, then that is going to correspond to the peak stress that you get if you looked at the stress at that peak there, because I'm evaluating it at 120 hertz. Okay.
Yeah.
If I did the same in random, then what you would find out in random, if I pick an element, plot it, and look at the stresses, that would equate to the RMS value here, unless I tell it I want it to be 3 sigma. That's how it works. So it wouldn't necessarily be this peak. It would be related to our spectral density RMS value, because it's a band. You know, it's a randomly generated spectra over that 10 to 2000 hertz. You can look at level crossing. There's other stuff you can do. There's other outputs you can derive from this. But again, that's maybe, for a more detailed, course or session would go through that. Okay. And conclusions. As you can see, or hopefully appreciate, it's maybe a little bit more complicated than just doing a linear static analysis, because you need to have an idea of vibration or dynamics, or what is damping, how do you apply it, what kind of spectrum am I doing it for, why am I doing the kind of simulation. You maybe need to have a little bit more of an awareness of what you're trying to do, rather than just a static analysis. You also need to have an idea of what the damping is in your structure. You need to start and interrogate the results to sort of see, well, what am I getting? Do I need to assume 3 sigma? Am I looking at peak values, RMS values, etc.? So you need to have an understanding of what that results is, or what the results are. The other thing that you'll find is that the results data that you generate will be large. Could be very large. So in my particular model, I mean, I haven't got a very big model relatively speaking, but my OP2 files are getting up to half a gig, and obviously you generate more and more data the bigger your models are. So size of data and manipulating of the data becomes significant, and also it can increase solution times to calculate what you're trying to calculate. So if you want to get the stress on every single element in your structure for a random input, then that might take a little bit of time. But that's like all of the ones that we've gone through from a structural perspective. The more complexity you put in, the longer the solution time is going to take. So that's why you might want to start and utilize symmetry if you can. Maybe start simple and then increase the complexity as you get an understanding of the structure. And for vibration, that's no different. You would do a normal modes to work out, do I really need to do the dynamic analysis? If I haven't got any resonances anywhere near the excitation, then maybe you'll get away with just doing the static stresses or scaling a 1G input to give you representative stresses. So you might do 1GX, 1GY, 1GZ, and then factor it by the acceleration that you're likely to see. And that's another way that you can do it. But in that case, you're not physically representing the problem as a dynamics problem. You're just scaling a linear problem because you don't because you assume you don't have any resonances that are interfering or changing the behavior of your structure. Any questions around what I've done there and the data that you've got?
I guess damping, Mark, is a whole other subject, isn't it? Because only true damping you get from testing, I believe.
Yeah, you get something that you can start and try and calculate damping and other parameters. So there are ways you can start and calculate it. But generally, the best way to do it is from test.
Yeah.
But it's understanding, the damping, the model, the assumptions that you're putting against it. But the purpose of what we've done today really is to show you the process and how would you access it and potentially use it to do a simulation. Most people might just do a normal modes and that might be sufficient.
But you can do material damping, can you, within this solution as well? That works off the material properties?
Yeah, you can get it to sort of calculate from the material property. You can have material or geometric damping. You can apply whatever you want to apply into it. You can also do stress stiffening, so you can have it where the more the cycles, the parameters will change as well. So you can do stress softening or stress stiffening. You can do a static offset and then calculate the frequencies. You can have contact in there with bolted interfaces, and that would give you some level of stiffness, and then it'll calculate the natural frequencies based on those preloaded contacted regions.
Mm-hmm.
So again, that's all part of what it could do. You could also use your nonlinear solver, which we did in session 2, to do a dynamics transient analysis in that as well. So you could do a transient analysis, but using the nonlinear solver as a function of time, but include the dynamic effects of your structure. It's another way that you could do it as well.
And how does that include damping then?
But what that will include is you can include the dynamic effects of it, but I think you define what the damping parameter is in the nonlinear solver.
Right.
Yeah. And that you can have different damping for different frequencies if you want as well, I think.
Yeah.
Rather than having the same damping for all. I think that would conclude the session unless, let's see if there's any questions or anything anybody wants to ask.
No, that was all good. Cheers,
In the next session, I think we got it wrong last week. We thought we had a break, but I think this time we do have a break. The next one I think is thermal, which is the 15th of March. And then there's a flow example, I think, on the 22nd.
Yeah, that's correct.
Yeah, is that correct? I thought I might have had them the wrong way around. So what we're going to do in those examples is start and look at, well, how do you do a thermal analysis? How do you connect your structures together thermally? What can you do to prepare your models in that way? And then the second one we'll be looking at purely sort of fluid flow, extracting volumes, pressure drop through systems, etc. Which again are core licenses that are available in tokens, but they're not available in a Nastran basic license. These are separate licenses that we're going to go into and use. Okay. I mean, if there's any questions come out of it, as we've said before, by all means, email Matt and he'll sort of coordinate them, and then we can send them back to you. Obviously, you've got the data, so hopefully you can start and take that and work with it. But you could, try your own structures in it and see how you get on.
Yeah, good. Thanks,
All
Mark.
right.
Right.
Thanks,
Thank you.
guys.
Cheers,
Thank
Mark.
you.
Cheers,
Thank you.
everyone.
Bye.
Have a good afternoon.
Bye.
Bye-bye.
You want to stay on, Mark?